Welcome to Data Science 1, Probability, Linking Probability to Inference, Part 1. Okay, some items we're going to need to remember. Sample space, random variable, probability distribution, sums of random variables, independently, identically distributed, Poisson distribution. All right, so we're going to try to go through an example here and show you how to fit all of this stuff together via an example without having too much theory involved. We're just going to try to take the ideas that we already know and apply them here. So, Bandula goes fishing every morning and catches several fish over the span of 2 hours before he needs to go to work. He records how much he catches each day by taking a picture, and I'm going to show you the data in a picture because I want you to see that the data isn't a number. Okay, so here, day one, this is what he catches. Then you count the fish for that day, and you get 5. Okay. Day 2, you count the number of fish, and there are 4. Here, he only caught 2 on day 3. On day 4, he caught 7, right? Let's make sure. 1, 2, 3, 4, 5, 6, 7. Correct. All right, on day 5, he caught 1, 2, 3, 4, 5, 6. And on day 6, he caught, oh my gosh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I think. Maybe I miscounted here. I think there's 10 or 11. Anyway, we're going to go with 11. All right, so we can turn this into probability if we make some certain assumptions. Okay, one fishing day does not influence the next fishing day. He's not fishing in a small pond where there's a limited amount of fish. He's fishing in a massive lake or ocean, and easily can, one fish isn't going to matter. Okay, each fishing day has the same probability distribution for the catch. So, for example, we don't know of any tidal shifts or fish migrations or anything like that that would increase or decrease the number of fish he could catch. And we're also going to put in here equal effort he's put into fishing every day. So he's conducting the experiment the same way each time. He's not just going out there and going, well, I got some fish left over from yesterday, so I'll just laze around today and relax, enjoy the waves, whatever. But here, so we have these assumptions that are going to have to be met. And if they are met, well, these are counts over time. So this makes all of these things here make sure that they're independent and identically distributed, right? These are the assumptions that make that hold. All right, so if we have that, well, we can try to calculate the probability of the data, right? That would be the probability x1 equals 1 because there's a random variable for each of the fish. Because before I pull it out, I don't know what the value is going to be, but I do know how I'm going to measure it. So the first measurement is x1, second measurement x2, so on and so on. So the first measurement is 5. So the probability of the first measurement is 5, second measurement is 4, third measurement is 2, fourth measurement is 7, fifth measurement is 6, and sixth measurement is 11. Now, these are independent events, right? One day doesn't influence the other one, so we can use the idea of multiplicative probability. So that's the probability x1 equals 5 times the probability x2 equals 4 times probability x3 equals 2, and so on all the way down to the probability x6 equals 11. Now, if we have probability distributions, which we do, a Poisson, we could simply plug this in. Now, notice I've left a lambda on each one of these. That's that same rate every day. And I'm trying to show that it's the same across each day, and I'm saying 5 given lambda. So the probability depends on the value of lambda. And then here I go through, I plug it into the distribution, do some simplification, and this is what I end up with. And here's the problem. It says, man, if we only knew lambda, we would be able to determine this probability. Okay, we're only missing a guess at what lambda is, and we could calculate it. All right, so we could guess a value and see what happens. So what happens if we let lambda equal 4? Why? Well, maybe 4 is a reasonable number, right? There's a 2, a 4, a 6, a 5. I mean, maybe 4 is a reasonable number. And if you do that, we take the formula from the last slide. Wherever we had a lambda, we just plug in 4. Plug it into our handy-dandy calculator and end up with 0.000000053. And so this is a small number. So the question is this rare? Is it common? Who knows? I mean, it's hard to know. So let's guess another value and see what happens. What happens if we chose 5? Well, what we'll do is we'll go back, take the formula we had on the other page, and we'll plug in 5. And this should be a 5 here. So don't panic over it. We just plugged in 5. Here we get this probability, 0.00000003. Wait, is there the same number of zeros? No, there's fewer zeros than there were last time. So that means maybe it's more common than the last one. So what we would do is just take a ratio of the two. Okay, that's an easy way of doing this, is just taking the probability of one and putting it over the probability of the other. And you can see the numbers next to each other as they're stacked on top of each other. And if you calculate this quantity, you'll get 6.1102. And you'll see that lambda 5 is 6.11 times more likely than lambda 4. Lambda equals 4. Now, wait a minute. This is an inference idea, right? We've made a conclusion that lambda 5 is more likely than lambda 4, so maybe it should be preferred? I don't know. But we're able to look at this and choose values of lambda, and we're starting to make conclusions about the value of lambda. And lambda is the parameter in the population. Okay? It's not the parameter in the sample. So we have to keep that in mind. We're now making an inference about the population from the sample. Okay, so can we find a value of lambda that would give a better ratio than all other lambda? And think about that. We could guess a lot of values, and that's what we're going to do right now. So if we can find the value of lambda that maximizes this probability, then this will meet that requirement, because no matter what I do, if I put the maximum on top, then it'll always be a ratio that's less than 1. All right, so what I did here is I just took this exact idea and I plugged in a whole bunch of values and I plotted it. So you can see what this looks like. And this would be a profile plot of a likelihood. And that's usually what this would be called, is the likelihood here. And what we did is we evaluated the numbers 4, and you can see how low it is here, and the number 5, and we evaluated it here. But you can see that there's even more to go. But this picture gives us the ability to see that, well, we probably need to increase it some. Okay, and if we do that, we can find that the maximum is here. Now all we need to do is figure out what number that maximum is, and that number happens to be 5.8333. This is going to maximize this profile of the likelihood. Okay, so this is what would be considered a maximum likelihood estimate. Okay, because we've maximized the likelihood or the probability of the data. This is the one that maximizes the probability of the data. All right, so if we have this, well, what have we seen so far? We have a whole bunch that we've learned out of this. We can take the probability distribution of a random variable associated with the actual experiment. Okay, a lot of people say, well, I'm going to just use the normal distribution because it's easy. Don't do something because it's easy. Do the right thing, and then you'll get the right answer. Okay? We can calculate the probability of the data given values for the parameter, right? We just did that. And with a little effort, we can find the best value of the parameter for the data collected. And the question becomes, can we find a systematic way of finding the maximum? And yes, we can. We'll do that in a later video. But here's the essential idea, is taking the ideas from probability and pushing them through until you can start making statements about the population parameter lambda. Lambda is what's governing the population. So what we want to do is make conclusions about that. And that's what we're trying to do. All right, so in the next video, we're going to start looking at another approach to this, guessing at these parameter values, and then we'll come back to this idea of maximum likelihood, and we'll see what we can get from there. All right, see you there.